Hello, and I welcome you all to the radiation lecture series. So in the previous video we have talked about the surface properties like emissivity, like reflectivity, absorptivity, transmissivity and all those things. And I have also shown you that how to uh, how to build a correlation between spectral hemispherical property. I mean, the most general thing is what? The most general thing is spectral directional property, and with this you can find any of the other things like spectral hemispherical, total directional or total hemispherical. Okay, I have shown you all the things that how can you find all those things. So let us solve a problem. Okay, so we will solve this problem. I hope that this is visible. It is saying that this one, that is question 4, a flat horizontal plate of a certain material at 1500 Kelvin, so temperature is given, has the following spectral directional emissivity. See, it is saying that it is spectral directional emissivity. The moment you see these words, that means you know that your epsilon you have to write by epsilon lambda dash, and that is a function of your lambda as well as theta as well as psi. Okay, and when it is exposed to air, that is fine. Now this function is given. Okay, this function is given like this, where theta is the angle of incidence measured from normal direction. I have shown you that when you are only concerned about reflectivity, then only uh, two angle comes. One is the angle of incident ray, another is the angle of reflected ray. But for any other thing like reflectivity, sorry, absorptivity, emissivity and transmissivity, our main concern is the angle of incidence, angle of the incident ray which it is making with the normal direction. Now it is asked that what is the total hemispherical emissivity of the material. The fractional blackbody emissivity power contained between 0 and n lambda t is given in the attached table. So I should have also shown you the attached table, but uh, I have the table in front of me. I will just show you that how it looks. So n lambda t. Okay, so another information it is given here. See, exposed to air. So for air, we suppose that n is equal to 1. Okay, so it is given that in the table n lambda t and f of n lambda t. I have shown already that, I mean, what is f. Okay, so those things I will not repeat anymore. So this thing will have the unit of micrometer Kelvin. Micrometer is for lambda, Kelvin is for T, N is not having any unit, and this is anyway a fraction, so this will not have any unit. Now see, here you will have many values, maybe 3000, 3100, 3200, 3300, then 3400 likewise, and corresponding to each value you will have a f value. For 3000 it is 27322. Okay, it is for 3100 it is 29576. For 3200 it is 0.31809. For 3300 it is 0.34009. For 3400 it is 0.36172. Clear? I mean, not only this much values, there can be at least 100 values like this. Okay, so now let us solve the problem. So first let me write the function of spectral directional emissivity. It is given as this is equal to 0.75, this one, for lambda less than 2 micrometer, and this is equal to 0.25 for lambda greater than 2 micrometer. Okay, So now I will copy this and yeah, I will copy this. What is happening? And I will put this here. I will again maybe copy this, put this here, this dash I will put here. So this is what is given to us, and we have to find, see, we have to find total hemispherical emissivity of the material. What is the total hemispherical emissivity of the material? The fractional blackbody emissive power is given in the attached table, and it is given that assume n is equal to 1. We do assume n is equal to 1 for air actually. Okay. So now let me solve it. So first of all, it is asked, so build a thought process. You are asked epsilon, that is neither a function of lambda nor of theta or psi. So, and you are given this. So how can you correlate epsilon with this? So what is epsilon? Epsilon is, so I am just doing it from the scratch again because I don't want you to I mean remember all those formulae. Okay, I don't want you to mug up this formula. Okay, mug up this large formula. So build everything from scratch. So this is what, if I write it again, this is total hemispherical emissivity. Okay, now emissivity is what? Energy emitted by the actual body at a particular temperature T by energy emitted by a black body at that particular temperature T. Now the moment you see two words total and hemispherical, that means those, I mean both of those energy emitted, that will be in the numerator and the denominator, those will be integrated over lambda because of this total work, and those will be integrated over the hemisphere all over the direction d lambda into cos theta because of this word hemispherical. Just only that. Okay. So now what we will write is, so in the numerator we will have IB lambda, right? IB lambda, or I was I think writing like this, IB lambda, then what? Then it is already a diffuse emitter, so this is not a function of theta and psi. Okay, and into all directions, so cos theta and sin theta d psi. This we know that this is our actually solid angle d omega, and also we have to multiply with d lambda. Okay, and we have to integrate from lambda equal to 0 to infinity, and also we have to integrate for the omega for a hemisphere. Okay, and for the above, now see, here will be what? Here will be I lambda dash. So this is actually what? This is the emissive radiation intensity. Okay, emissive radiation intensity. So this is the radiation energy contained by a radiation ray which is emitted by that surface at that particular temperature. So emissive radiation intensity of that surface. Clear? So now this is a function of lambda, t, theta and psi. Again we have to multiply a cos theta here, and obviously d omega, and this d omega is nothing but, we know that sin theta d psi. Okay, and also we have to multiply with d lambda. We have to integrate from for lambda equal to 0 to infinity and over the hemisphere. This is the basic definition of total hemispherical emissivity. Clear? So now you will argue that okay, but in this definition I am nowhere having epsilon lambda dash, the spectral directional emissivity. So how can I have that? See, now you go to the basic definition of spectral directional emissivity. So spectral directional emissivity, it is a function of all the things lambda, t, this and this, theta and psi. It is defined as the same thing, that is the energy emitted by a particular body, particular surface. Okay, but now we don't have to integrate. Okay, we don't have to integrate because it is spectral directional. It will depend upon the direction as well as upon the wavelength, and it will be compared with the black body thing. Okay, this is the definition. So from this definition we can write this I lambda dash is equal to I v lambda into epsilon lambda dash. Clear? So you have to put this thing here. Okay, so let us now do one thing to save our time. I will not write this whole thing again. So what I will do is I will again copy. So it would be great, right, if we are allowed to write our exam in a iPad like this, then we don't have to write the things again and again. We can just copy and paste. Yes, I mean there is nothing wrong with that if the internet connection is cut out. Okay, if the internet connection is cut out, then it is fine, right? So now I will just replace the things. Okay, so with instead of this I will write epsilon lambda dash into I v lambda. Okay, and now let me replace the d omega also, cos theta sin theta d psi d lambda. Clear? Okay, so now we know that this I v lambda is not a function of theta or psi. Okay, so here there will be one d psi also and then d lambda. Okay, so that means for both of these what I can do is, okay, so let me solve first the denominator. I mean I have already solved this. So what I can do is I can write this denominator. Okay, so I am writing this as my numerator by denominator. Okay, so denominator is this one, I v lambda. Okay, I will only integrate with respect to lambda here, 0 to infinity. Okay, and there will be a pi, just a pi, because we know that this part, that is if I am integrating over the hemisphere, then my cos theta sin theta d psi, this becomes my pi. Okay, I have already done this. In the previous video I have made some mistake of not putting this cos theta everywhere, but I have also rectified that mistake in the previous video, right? Okay, so that means this actually becomes pi into this much, right, I v lambda, this one, obviously at a particular temperature. I mean this I v lambda is a function of lambda and t. Okay, so maybe I should write that it is a function of lambda and t, it is integrated over d lambda, yes, lambda. So now if we apply the Planck's distribution, then we will have this is equal to pi into sigma t to the power 4. Clear? So this is our denominator. Now what about the numerator? So numerator is what? Numerator, let me write this separately. So this we are integrating over the hemisphere and lambda is equal to 0 to lambda. We are having epsilon lambda dash into I v lambda, then cos theta sin theta d psi d lambda. Okay, now again, okay, so now this thing is not a function of theta or psi, but this thing is a function of lambda, is a function of theta, and is a function of psi. But now I know this function. Okay, So what I can do is, see here I am given two ranges of lambda. One is lambda is greater than 0, less than 2 micrometer. Another is lambda greater than 2 micrometer, less than infinity. So try to grasp my thought process. Now I know these two ranges of lambda, and in these two ranges of lambda I know explicitly my expressions of epsilon lambda dash. So what I will do is I will break I will break sorry I will break this range from lambda 0 to infinity to, I will break into 0 to 2, then 2 to infinity. Okay, so I will write like this: 0 to 2, okay, 0 to 2 micrometer, and then my epsilon lambda dash is what? Epsilon lambda dash is your, that is given, right, 0.75 cos theta, right. So it is 0.75 cos theta, okay, and I will write, okay, the same thing, IB lambda cos theta sin theta d theta, okay, this thing I am having, okay, plus I can write, and also I have to integrate over the hemisphere. So plus I have to write from 2 to infinity. Now it is given as a constant, and that constant is 0.25, okay. So it will be 0.25 IB lambda cos theta sin theta d psi d lambda. Clear? Okay. So now let us see. But you still have to take care of this fact that this is a function of lambda anyways. But now uh, in this expression I have this was I have this thing also as a function of lambda, but now in this expressions, this and this, I have only this IB lambda as a function of lambda. Now uh, written the explicit expressions of epsilon lambda dash, so I don't have to worry about that, okay. That is, now this is not a function of lambda, and this is also not a function of lambda. So now what I can do is I can write it like this. So 0 to 2, 0 to 2. Now what I will do is I will put, so over the hemisphere theta is equal to 0 to pi by 2 and psi is equal to 0 to 2 pi, okay. Now you have to do this integration, 0.75 cos square theta sin theta d psi, okay. This whole thing is a constant into IB lambda d lambda. Then you are integrating, okay, then you are integrating from 0 to 2 plus again integration from 2 to infinity. Then again you will be having psi is equal to 0 to 2 pi, theta is equal to 0 to pi by 2. Now you have 0.25 cos theta sin theta d psi, clear, and then IB lambda d lambda, clear. So here you see, here your this thing total and this thing both are constants. Even this constant, you know, this is, if you take out this 0.25 outside the integration, you will get as 0.25 into pi, but this you have to do, you can take out this 0.75 out of the integral, but then also you have this thing, but still you can do this integration very easily. So first of all, this integration you can break into two parts. For d psi, it will be 0 to 2 pi integration of d psi, that is equal to 2 pi. With that you will have into from 0 to pi by 2 cos square theta sin theta d theta. So here you can take one thing, cos theta as your z, then If you differentiate both sides, then your minus sine theta d theta will be your dz. So this thing will be minus dz and this thing will be z square. Clear? So then you can evaluate those integrals very easily, so I am not doing that thing. So here what I will do is I will term this as my a1 and this as my a2. Clear? So then I will have, see, a1 into 0 to 2 ib lambda d lambda plus a2 into 2 to infinity ib lambda d lambda. Clear? This is what? This is my numerator. Okay, that means now my epsilon becomes this thing, only this thing, sigma t to the power 4, or I can write like this, sigma t to the power 4 means what? My your ib lambda or pi ib lambda d lambda. Okay, so I think these are clear. Okay, so this is sigma t to the power 4, that is fine. Either you can write sigma t to the power 4 or you can write pi ib lambda d lambda. Okay, so now you have to take care of just one thing, that is the f function, that is f of n lambda t, that is the fractional black body emissive power. The moment you say fractional black body emissive power, okay, that means you are talking about this thing 0 to infinity and not this thing. Okay, that means my f lambda t n lambda t, this mistake also is very common. This is eb lambda d lambda from 0 to infinity. Okay, emissive power 0 to lambda at a particular temperature T. Okay, and by 0 to infinity eb lambda. Okay, it can be either of this or this, that will so it can be this, and also now you can argue that it is also equal to this. Okay, because eb lambda is nothing but pi into ib lambda. Okay, so people in many times think that okay, so I am given this, so then how can I find? If I am given this, then how can I find this? The ratio of ib lambda. If I am given the ratio of eb lambda, then how can I find the ratio of ib lambda? It is just a factor of pi, and that will be cancelled out. So both of these are equal. Okay, so these subtle things you should take care. Okay. Okay, so I will write this like it. Okay, so epsilon, this thing becomes your array. Okay, I will write like this. This becomes this. Okay, so a1 0 to 2 ib lambda d lambda plus a2 2 to infinity ib lambda d lambda. So why I have told you that thing, the comparison between eb lambda and ib lambda? See, because if you have written here instead of this thing sigma t to the power 4, then you cannot write that this is equal to f of n, that is 1. Okay, so let me write it clearly. So this thing is equal to, I can break it, a1 by pi, I can take that out, 0 to 2 I b lambda d lambda by 0 to infinity I b lambda d lambda plus a2 by pi 2 to infinity, okay, this thing by 0 to infinity I b lambda d lambda. Okay. So now this is the answer, and here we know that our t is equal to, so this is equal to actually f of n lambda t. So n is equal to 1 and here lambda is equal to 2, t is given as 1500 Kelvin, and this is again equal to, okay, so now this is what, 2 to infinity. So that means I can write this integral as what, 0 to infinity of this minus 2 to infinity of this, because you see you have f of n lambda t is equal to the fraction of 0 to 2 I b lambda d lambda, okay, or 0 to lambda by 0 to infinity I b lambda d lambda. This is another mistake. People again people will again write here 1 into 2 into 1500. No, this will be what? So I am going very, I mean, slowly, okay. So this will be what? This whole thing will be 0 to infinity I b lambda d lambda minus 2 to infinity I b lambda d lambda by 0 to infinity I b lambda d lambda. So this becomes 1 minus 2 to infinity I b lambda d lambda by 0 to infinity I b lambda d lambda, right? That means this is equal to 1 minus f of n lambda t, n is equal to 1, lambda is equal to here 2, sorry, I have written a bit. This is not 2 to infinity, this is 0 to 2, 0 to 2, this is also 0 to 2, okay, still 1 into 2 into 1500, okay. That means my answer is, finally my answer is a1 by pi into f of 300, okay, plus a2 by pi into 1 minus f of 300. Clear? If I have not made any silly mistake. Now you see, people will make one mistake here. So they will write instead of this here sigma t to the power 4. That is fine. But then again here you will have sigma t to the power 4. But this is not equal to, okay, I mean the moment you will have sigma t to the power 4 here, you will not have your pi here, because you have taken this pi inside the integral, and that is how you write this as your sigma t to the power 4. So now you have your this thing a1 into 0 to lambda I b lambda d lambda by sigma t to the power 4 plus a2 into 2 to infinity I b lambda d lambda by sigma t to the power 4. But now my 0 to 2 I b lambda d lambda by sigma t to the power 4, this is not equal to f into f of 1 into 2 into 1500 Kelvin. This is not equal to this. This is not equal to this. Okay, you have to be very careful. So what you have to do is you have to multiply a pi here and multiply 1 pi here. Then this becomes Eb lambda d lambda 0 to 2. Then this is equal to this fraction. So those students, I mean, who will put here this thing, okay, and they will take this whole thing as my f function, they will miss a pi, they will miss this pi. So their answer will be actual answer into pi. That is wrong, okay. So be aware of these mistakes. So I think you have understood that how to find total hemispherical total hemispherical properties given directional spectral properties. If it was given absorptivity, then what you would do? Then from the definition of spectral directional absorptivity, this would be alpha lambda dash is equal to I I I that is absorbed IA lambda t theta psi into I incident, or that is I we write as G. Okay, so then here you would have epsilon lambda dash into G, and here only G. Okay, these are the basic things. Okay, basic concepts. So you should build your concept like this. I don't want you to mug up this formula. I mean, people in GATE, okay, in exams like GATE, people try to mug up this formula. But why? I mean, why do you need to mug up this? I mean, hefty formula? Already we have so many problems. We have to pass examinations. We have to take care of our girlfriends and boyfriends. We have to take care of our family, neighbors, blah blah blah. So many things. So why do you take another thing, that is mugging up this formula? You mug up only this definition. Yes, this is another definition that we have to mug up. But you tell me that, I mean, what is easier, to mug up this definition or to mug up this definition? Okay. Okay. So this was one problem. Now I will move on. I will solve also, I mean, more problems. Okay. And this problem also is having another parts. You can also try. Okay. Okay, so this is another part. If I get time in this lecture, then I will solve this. See, if sun at 500, if sun at 5700 Kelvin radiates this surface at an angle of theta equals to 45 degree of normal, what is the relevant total absorptivity? Okay, so you try this one. Okay, you try this one, you pause the video and try this one. If I get time, I will solve this in the end of this video, or if I don't get time, then I will solve this in the next video. Okay, but now let me proceed and introduce a very important concept, that is the concept of what? View factor. View factor. So this concept is very much analogous to the examination hall. So in the examination hall, we cannot look into any other answer script like anything. Okay, so what we need to do is, we need to adjust our eyeballs, not our head. We cannot turn our head, then the guard will catch us, then the invigilator will catch us. We have to adjust our eyeball, we have to rotate our eyeball. So in this case, we wish that if I was a lizard, if I was an animal who can rotate his two eyeballs, I mean 180 degree apart, then it would be much easier to cheat in the examination. But we cannot do that because we are humans. So we have to adjust our eyeballs in such a manner that we can see the answer script of my friend who is sitting beside me, I mean, as much as I can. Okay, so but due to the space constraint, you cannot see the whole copy. You can only see a part of the copy. Okay, so your friend is trying his or her best to make you see his or her copy, but because of the space constraint as well as your biological constant, because you cannot, I mean, rotate your eyeball like anything, you are only getting a particular spectrum or a particular part of your friend's copy. Okay, this is the concept of view factor. That is, view factor is how much of your friend's copy you can see in the examination hall by the total copy that your friend is trying to show you. Okay, so now just let me just call let me just call your friend as DAI. So this infinitesimal area is your friend. Okay, and your friend's copy is oriented at a particular direction, your friend's copy, and your friend is sitting as per the sitting arrangement. So that will determine that, I mean, what is the normal. So this is the normal of DA, and this is U. Okay, this is U. So okay, this is you are DA J, infinitesimal area J. Because of the seating arrangement, your normal direction is NJ. Clear? And this is the distance between you two. This distance is S. Clear? And another geometric figures also, you guys know that these angles are these angles are theta I, and this angle is theta j. Okay, these angles are theta I and theta j. Okay, so I have already told you that this is your friend and this is you. Okay, so my view factor is described as F DAI DHA. Okay, so this is defined as, okay, total energy emitted by DAI, and this is total energy total energy absorbed by DAJ out of total energy emitted by DAI. Okay, so all these words are important. You cannot just write total energy absorbed by DAJ, because DAJ can absorb energy from any other source also. But when you are talking about the view factor F DAI DAJ, then you have to take care of the absorbed energy by DAJ, which is coming from DAI only. Okay, so like if you are sitting here and here is your one friend and here is your another friend, so you are J and this is I, this is K. Okay, so you can cheat in the examination from K also and from I also, but I am talking about of this pair, that is, how can you cheat from your friend I? Okay, so that is the thing. Okay, I mean, how much can you cheat from your friend I? That fraction. Okay, so let us calculate again this numerator and denominator separately. So total energy emitted by DAI. So this is equal to, we assume that my I lambda dash. Okay, so let me tell you that we are doing this analysis for a diffuse gray body. Okay, diffuse gray body or diffuse gray surface. There are other analysis, other very in-depth and detailed analysis for non-diffuse non-gray surfaces also, but in our scope we are not doing that. Okay, So here actually this is not a function of then lambda or theta. So this will be only a function of t. Okay, is it so? No. See, I have done a mistake. So I cannot write diffuse gray surface. I should write diffuse gray emitter, and absorber. Okay, and absorber. Okay. Actually, this is a, I mean, consequential fact that if it is a diffuse gray surface, then my epsilon is I mean my epsilon lambda dash is equal to epsilon. Okay, that means I mean whatever it will diffuse, that is my I lambda, dash is equal to IB lambda into epsilon lambda dash is equal to IB lambda into epsilon. Okay, now see, you can argue that okay, this expression is not a function of direction, because neither my epsilon nor my IB lambda is a function of direction. I agree with you, but your IB lambda is a function of lambda. So diffuse surface does not mean it will be a diffuse emitter. Okay, diffuse surface does not mean it will be a diffuse emitter. Diffuse surface means emissivity is same. Sorry, what, I am extremely sorry. Gray surface does not mean it will be a gray emitter. Okay, we have seen that diffuse surface will mean that it will be a diffuse emitter, that is true, but gray surface does not mean that it will be a gray emitter. Okay, because you see here this epsilon is not a function of lambda being a gray surface, but this IB lambda is a function of lambda. That is why for a gray surface I can be a function of lambda. But whenever you are saying that gray emitter or diffuse gray emitter, then I am saying diffuse gray emitter and absorber means the emitted energy or the emitted radiation intensity will not be a function of lambda. Okay, so this will be, I should write, or okay, that is fine. So total energy, okay, this is I am writing only I is a function of t into dAI, but now I have to take the projected area, because I am interested at how much energy dAI is emitted. Okay, no, sorry, this will be cos theta, because this is total energy emitted by dI, so I have to integrate throughout the directions. So dAI cos theta sin theta d theta d psi and also d lambda. Okay, so for the sake of for the sake of generality, we take that this is a function of lambda also. Okay, but generally we don't do that. Or if it is not a function of lambda, okay, sure. If it is not a function of lambda, then we don't need to integrate this. Okay, or you can say that it is, this total analysis is done at a particular lambda, at a particular wavelength, because see, view factor has nothing to do with lambda. I mean, it is true for any lambda. It has only to do with the distance, that is this s, and the orientations of the surfaces. So distance between the centroid of the surfaces and the orientation of the surfaces. So this will true for any lambda. Okay, this will true for any lambda. So be it a gray surface or not, that will actually does not matter for the case of view factor. but that concept still remains true, and this is a very important concept. So in any interview they can ask you, does a gray surface means that it is a gray emitter? No, no. The emissivity is the emissivity is not a function of lambda, but I cannot say that it is a gray emitter because there is IB lambda. Okay, so here I will say that this is a function of lambda. I don't care, but I will not integrate with respect to lambda, because even if I integrate with respect to lambda, then also the total thing will be same. Okay, then also the total thing will be same. So here it will be, then also the total analysis will be same. So it is at a particular lambda, and therefore I am not integrating with respect to lambda. You can integrate, but there is no meaning of integrating because it is the same analysis for any lambda. So first you do the analysis, then when you will be solving the problem, then you can integrate. So I will show you that what I am meaning by that. Okay, so this is the total energy. That means I have to integrate over the directions. So integrate over theta and psi, and over the hemisphere, so theta is equal to 0 to pi by 2, psi is equal to 0 to 2 pi. Okay, so now this will again become, so dA I can take common. Okay, and I lambda T lambda I can take common because this is not the functions of direction, and we already know this integration, this will yield pi. Okay, so this is the denominator. And what about the numerator? The numerator would be, see, energy absorbed by dAj from dAi. Okay, so let us first do it for the single radiation ray I. So I is coming from dAi to dAj. Clear? So firstly, then I need to see, so my objective is I have to find that from this point, because this is an infinitesimal area, it is as good as a point. From this point, how much is going in this area? From this point, how much is going in this area? So it is saying, it is as good as asking that how much radiation rays are there that is cutting this area. That means the concept of solid angle comes. Okay, now again I have to see that how much, now this is you, or sorry, this is your friend. Okay, so now your friend is supposed to orient his or her copy so that you can see the copy easily, but your friend also is seeing you at a particular manner. So your friend also not seeing you totally, your friend is seeing your projection in this direction. Your friend is seeing your projection in this direction. So I have to find that how much radiation ray is being contained within the solid angle, that is subtended by this dAj projected in this direction at this point. I am repeating this sentence again. So I have to find that how much radiation rays are there within the solid angle that is being subtended by the projected area of dAj in this direction at this point. Clear? And that is nothing but your dAj projected by a square. This is the definition of solid angle. Solid angle subtended by dAj projected at this point. And dAj projected means what? dAj into cos theta j. Clear? So here I am writing, so it will be dAj cos theta j by a square. So this total term is nothing but your d omega. I should write j projected, that is solid angle subtended by this daj projected. Okay, fine. But again, how much, I mean, this radiation ray is going like this. Okay, so there are so many radiation rays, so you have to integrate, right? Likewise, you integrated to find this total energy throughout this direction. Again, you have to find that throughout these all these, I mean throughout all these directions, how much energy is leaving, and from that energy how much is contained in this much solid angle. Okay, so I have only done this. I mean, if I am just writing this much part, then I am writing this for only one radiation ray in only this direction. But now I have to write for all these directions. Okay, so that will be cos theta I. Okay, cos theta I mean that will be into cos theta I into dai. Clear? So this is the part. Now this much energy, so I mean, so let us again see the part step by step for this one. So this is the radiation ray that is going in this direction. Okay, so to account for that, I have to write this much into the dai projected, because I have already told you that I have to take care of the projected area for this also, because from this the radiation ray is coming. Okay, so when I am writing this, to take care of this direction factor, the total energy that is going from this area in this direction, that is equal to, you will see, I mean I think you will appreciate this expression, that is, this will be I lambda, that is a function of lambda of t, into s dot ni dot. I have to include this term to take care of this direction factor. So this much part is energy emitted by your friend, the copy emitted by your friend, or the energy emitted by dai in the s dot direction. Now out of that energy, how much will be contained under the solid angle projected by d omega jp? For that we have to multiply this. Clear? So then my f dai daj becomes what? Your I lambda, that is a function of t and lambda, I am not writing that again, daj dai cos theta j cos theta I by, there is one s square and this whole thing, that is pi dai I lambda. Okay, that thing only. Clear? So then clear, that is fine. So this thing, I mean now which things I can cancel out. Okay, Now actually I need to integrate this thing. Okay, actually I need to integrate this thing, because I have to take care over all the directions. Okay, I have to take care over all the directions. And why that is so? No, okay, let it be. Let it be. Okay, this is the answer actually. No, don't more. We don't have any complication other than this. This is the answer. This we will cancel out, and di will be cancelled out. Okay, so this will be daj cos theta j cos theta I by a square into pi. Clear? This is the answer. But these are for infinitesimal area. Now can you tell me that what will be ai daj? This will be what? So I am telling that we have a finite area ai and we have a very small area daj. That means now there are so many parts through which the radiation rays will go out. Earlier we have only one point because dai is as good as a point. Okay, but now we have so much points. So then we have to integrate over this I thing, over this theta I and theta j. So you don't make the mistake of integrating on this expression. You have to integrate over this expression. Okay, so this thing will remain same, that is a square pi dai into I lambda, but this thing will be, let us see, so it will be integrated over the whole area ai and over the uh, whole direction also, theta. Okay, so this will be your I lambda daj dai cos theta j cos theta I. Okay, so then you have to do this integration over ai. So this will be the answer. Clear? So now can you write the expression for dai to aj? Can you write the expression for f of dai to aj? That is your homework. Okay, and finally you have to write f of ai into aj. Clear? So these concepts are very important. Okay, and I have also told you that I will solve the other question in that thing, in that question paper. Okay, let me write this thing. So this is f dai daj. I have a little bit time, so I was thinking to give you as your homework. So one expression you have to write, that is f dai to aj, but this thing will be what? This thing will be ai aj I lambda daj dai cos theta j cos theta I a square pi dai I lambda. Now if I take the assumption that my I lambda is uniform throughout the surfaces, surfaces ai comma aj. Clear? That means I can take this I lambdas out of the integral, so then these will cancel out. Okay, so finally this is okay. So here you are taking that ai, that means I have done one mistake. Here also I have to integrate over ai, and here also I have to integrate over ai. So that means I will write this thing, and this thing is nothing but your ai. So finally if I write for the finite areas, f ai aj is equal to your ai aj. Okay, dAi dAj cos theta I cos theta j s square pi ai. Clear? This is the answer, but still one expression is remaining that you have to write. Clear? Okay, so finally, see, now can you write just one final thing? If AJI, sometimes you also have to I mean help your friend, right? So that will be, so you just swap AJ and AI. AJ, AI, DAJ, AI, cos theta j, cos theta I, s square pi AJ. So I think it is very much visible from this expression and this expression. You just tell me if it is absolutely clear or not. That is Fi into AI into F AIAJ is equal to AJ into F AJAI. If it is clear, then my friend, you have learned the reciprocity relation. Reciprocity relation of view factors. This is one of the most important results. Okay, without this you will not be able to solve any problem in radiation. Okay, so just one more time I will give you the explanation for this, because I think this is a bit confusing. So we have to find the energy absorbed by dAj, but not any energy, the energy that is coming from dAi only. So here di is a infinitesimal area, as good as a point. We take this as the point. So from this point there can be so many directions through which, infinite directions through which energy can be emitted. But I am interested that what is the amount of energy that is emitted only in this direction. Only in this direction. Now in this direction I can have a solid angle. In this direction I can have a solid angle. Okay. Now in this solid angle, how many radiation rays can be there? That is the basic concept. So this I lambda, where was, okay. So this I lambda T lambda, although I am telling that this is a diffuse emitter, but this is energy emitted, or this is the radiation ray at a particular direction. This can be this direction, but when I am talking that, I am concerning that only in theta I direction, that is, this is my Ni, this is my S cap. So I am talking that if I have to find the radiation flux in my S cap direction, that will be my I lambda T lambda into Ni dot S cap. This Ni dot S cap is cos theta I, and this is per unit area, so I have to multiply dAi, although it is only a point. Then this is the radiation ray per unit solid angle, because we haven't taken care of the factor that there can be a solid angle also. Okay, now solid angle subtended by, not by dAj but by dAj projected, this I have shown you, that I have to see that from this point I cannot see this whole area. From this point I can only see this much projected area. Okay, according to that your friend will orient his or her copy so that you can see that, right? So this projected area is dAj into cos theta j, and so a solid angle subtended by your projected area at this point, that is dAjp by S square. So that is nothing but this part. That is nothing but, where was it? This part. So multiplied by this, this is the total energy that is radiated from dAi in the direction of dAj. Okay, and that is subtracted by dAj. So, okay, I mean that is subtended by dAj. This much energy is absorbed by dAj. Okay. So I think that much is okay for now. Okay. So this was the concept of view factor. Now I don't have much time. Okay. So we will see the other things. I mean, I will solve the problem in this question paper. The second problem actually, this problem. I will solve this problem in the next lecture, and we will see. I mean, many more things about the view factor is remaining. I will talk about those things in the next lecture. So until that, goodbye, take care, and thank you.